and inner product and norm. So the inner product was defined like that. And we define orthogonality to mean, so two vectors are orthogonal if their inner product is 0. This has the usual geometric interpretation. So two vectors are orthogonal if, when you look at them, they form a right angle. And then we define what it means to be orthogonal to a subspace. So a vector is orthogonal to a subspace if it's orthogonal to every element in the subspace. And then you can also define orthogonality of two subspaces by saying that so V1 would be orthogonal to V2 if every vector in V1 is orthogonal to every vector in V2. Then we define the orthogonal complement, which is sort of the largest subspace that's orthogonal to V. So it contains a set of all vectors X that are orthogonal to V. So if you have a subspace V, even if it's not a subspace, actually you can define this V pair. So for any subset of Rn, you can look at the set of all vectors that are orthogonal to it, that V pair would be well defined, and it would be a subspace. If V itself is a subspace, then you go to V perp, and then we perp back. So the orthogonal complement of the orthogonal complement gives you back the V. And then we did some sort of simple example that if you have the XY plane, the orthogonal complement would be the Z-axis. If you have the Z-axis, the orthogonal complement would be the XY plane. And you can sort of prove it or do it the algebraic way by looking, for example, this matrix, the image, which is the span of the columns, is the XY plane. And so if you want to compute the orthogonal complement of the XY plane, you can try to compute the orthogonal complement of the image of X. And the orthogonal complement is the set of all Z's that are perpendicular orthogonal to V. And this, if you think about it a bit, is equivalent to being orthogonal to every column of V, because everything in V can be written as a linear combination of the columns. So it's enough to be orthogonal to X1 and also orthogonal to X2. So if you write down these equations, these are inner products, certain inner products equal to 0. It gives you two equations in the coordinates of Z. So Z here would be let's try. Z would be Z1, Z2, Z3. And it forces the first two coordinates to be 0. The third coordinate can be anything. So you prove that the V pair is the set of all vectors that looks like that, or the span of 0, 0, 1, which is the Z-axis. Okay, the Z is not the same as the Z above, but okay. Yes.
If we had a question like this, do you prefer the first notation or the second notation of the span?
It doesn't matter. So the equivalent, as long as it's correctly specified. Yeah. Good question. Any other questions? Okay. Then we define the norm. So based on, if you have an inner product, you can define the norm of a vector as the square root of the inner product of that vector with itself. If you expand it, it's just basically the root of the sum of the squares of the elements of X. And so this norm is intuitively the size of a vector. So if you imagine a vector being like something that's drawn from the origin to the point X, the length of that vector is like given by this norm. And if you have two vectors, X and Y, the length of the difference tells you something about the distance of the 2 points, so X and Y. So you usually think about X and Y as both like points and sometimes as like arrows. Most of the time as points. But so the distance of these 2 points, X and Y, is the norm of the difference. And then there's this identity that I encourage you to verify. So the norm of difference squared, you can expand because this can be written as the inner product of x minus y with itself, and then you can expand the inner product. So like a minor comment here that the terminology. So inner product is bilinear. So a bilinear form. Does anyone knows what bilinear, what I mean by bilinear form? So what I mean is that it's linear in both elements. So if I fix this, it's linear in this part. So for example, if I have like x and u plus v, these are all vectors, the inner product would expand like this, x and u plus x and v. The same goes if I do the other way around. So if I do like u plus v and x, so it gives me like u x plus vx. And so if you have, for example, u plus v, and then u plus v, so you can expand. Like u plus uv, or it's like, let's do it the other way. So this and x plus y, these are all vectors. So you get ux plus uy plus vx plus vy. The same goes with the scalars come out. So that's sort of bilinearity. So you can expand in a linear fashion. And if you do this here, there's also symmetry. So the inner product of xy is the same as yx. So xy is the same as yx. If you look at the definition, it's symmetric. So if I change the order of x and y, it doesn't matter. So using the bilinearity and symmetry is a bilinear symmetric form. You can do this calculation, okay? Sort of, this is inside parentheses. There's another thing which is a symmetric bilinear form, and that's the covariance operator. I'm going to talk about that later, okay? So a lot of things in mathematics are interesting objects are symmetric bilinear form. Sounds good? This terminology is easy to remember. Might be a little bit harder to recall what it means, but if you remember symmetric bilinear form, it has a lot of information. Inner product is a symmetric bilinear form, or a bilinear symmetric form. Better to say symmetric bilinear form. So, questions? Let's take this out. Let's do it here. Okay. Symmetric bilinear form. Okay. Symmetry is this. Bilinear is that. Okay. So use this to like expand this and then show that this result holds. Questions? Okay, so that's enough warm up, I guess. So what I want to talk a little bit about, and which is going to be very important for us, is this idea of projection. So let's see how many people know. So let me use this new feature. So I'm going to tape this so that you don't see what this is. Then ask you, what is projection? Anyone knows what have you seen projection of a vector onto a subspace? Okay, so yeah, you want to go?
It's like the shadow.
Okay, good. Yeah, like intuitively, if I like have a subspace, the shadow is a little bit like, if like the sun shines perpendicular to it, would be the shadow. But if it like shines from the side, the shadows are more complicated. But it's like if you have a vector and then there's a light source directly above, and just like the light shines perpendicular from above, then the shadow would be that. Yeah, the light source is here, it's going to be different. But that's good. That sort of tells you like some intuitive, in some intuitive sense, what the projection is. So the projection of this in this space would be that. So any more. So this is what I'm talking about is orthogonal projection. Orthogonal projection. So any more insight? So if we want to define a projection. So let's say I have X and I have V. This projection, let's call this X hat. It's going to be another vector. So what do we know about this, or how can we define it? Or, yeah.
It's like the shortest distance you can get before that orthogonal complement.
The shortest distance. Yes. Okay, great. So if you look at this, that's a definition that works. If you look at this distance, okay, so first X hat is some vector in like V, right? We're looking for a vector or an element in V. Basically, intuitively, we want to represent X by a vector in V. Okay, so the information that we have is V. This X we want to like approximate or represent by something in there. We want to be as close as possible to X. Okay, so think of projection as approximation would help. So want to approximate X by a vector in V. So look for best approximation. Best here means closest to X. Okay, so what you do is like going to minimize. I'm going to look at distance X minus Z, pick a generic Z here. So let's say this could be Z, this could be Z, or this could be Z. I'm going to vary Z here in the subspace and look at the distance. So the distance, the X minus Z would be this difference. The difference, the norm would be basically the distance of Z and X, right? So the length of this would be, or in this case, the length of this or the length of that. So this is the distance between the approximation, which would be Z and X. So we want to minimize this, okay? And I'm going to use this notation, argmin. The argmin would be the projection. So argmin means the argument that minimizes this. So the Z that minimizes this would be the projection. Okay. So in other words, so this is equivalent to saying that the distance of X hat minus X, or the other way around, let's write it. X minus X hat is less than or equal to X minus Z. If you recall this notation for all Z in V. Okay. So among all Z's that I can pick in V, X hat is the one that has the shortest distance to X. Or the error, if you want to call this, the error is the smallest. So this is the error. Okay, if I call this E, this error for different vectors, it would be different. So for this guy, it would be like this. This would be E prime, let's say. So the length of this, you can see intuitively that this is bigger than the other one. So as I vary, I change it until this is the smallest. At that point, the vector in V is the projection. Does that make sense? So think of projection as approximation. Best approximation from a subspace to a vector, which is potentially outside. This is the easiest or like most, I would say, informative way of thinking of projections. Okay, so you have like some restriction. V is your restriction. So you're bound to choose from this set, but you want to like reconstruct as close as possible. But you don't have freedom to go like as like close to X as possible. We're going to go as possible within our constraint, which is V. And that would give us the projection. And the whole idea of regression is this. Okay, so you have a model which is going to be this V. You have an observation which is like Y, and then you're going to find the best that your model offers to approximate Y. That sort of, we'll see that sort of nicely captures the geometric idea behind linear regression. Okay, sounds good. So this is, let's say, definition. So this exists. Solution exists. Solution exists and is unique if V is a linear subspace. At least. If V is a more exotic object, sometimes you can still say that it exists as unique. Just in parentheses, if it's a closed convex set, the projection still exists. But all the things that we talked about are going to be for linear subspaces. For linear subspaces, the projection is unique and it exists. And in this case, it's going to have a very intuitive characterization. So there's an equivalent characterization that I can use to specify the projection. So what is that intuitive characterization? Is there some very special property of this E that they can use to characterize the projection? Yeah. Yes, great. So E is going to be orthogonal to X hat, but it's orthogonal to more, not just X hat. Yes, E is going to be orthogonal to the subspace V, to the entire subspace. So in the case of where V is a linear subspace, which is going to be the case for us in this course, and equivalent characterization, of projection X hat is that the residual, let's call this residual E, which is like X minus X hat, is orthogonal to V, i.e. E, which is X minus X hat, is orthogonal to V, if you remember the notation. So this is a characterization. What I mean by characterization, it's if you find an X hat such that the difference is orthogonal to V, that has to be the projection. The projection is the only vector that satisfies this, sometimes called orthogonality principle. Orthogonality. Principle. Okay. Sounds good. Okay. Another way of saying this, if you remember what perp is, this is equivalent to saying that E belongs to V perp. Okay. V perp is the set of all vectors that are orthogonal to V. So it's saying that the residual belongs to V perp. Okay. So if you think of the space, let's say this was the XY plane. If I pick any vector here, and then I project it, basically this E has to be orthogonal. So I'm going to go down perpendicular. So this is E. It's X hat. And you can see that, let's say the origin is here. This is Z, the Z axis. And you can see that E that belongs to this. So I think of this as a vector. As a vector, E, so you have to think of usually you think of the vectors as like origin is like here. Okay, so this is really E. So E is in the perpendicular, like the V perp. So E belongs to V perp, which is the Z axis in this case. If V is XY plane, the XY plane. Okay. Similarly, if you think a little bit about this, what would happen if I try to project X onto this Z axis? What do you think would happen? Sorry? Yeah, so if I project now X to the Z, the projection would be E, right? And this X hat would be the residual. So in that case, if I project it like that, this would be now my, like, call it X hat hat if you want. And then the residual would be the difference between this and X, which is that guy. That would be E hat hat, which is just the same as this. Okay, so really the role of the two would interchange. Okay, so in general, I can write X as X hat plus E. This would be in V, and this would be in V perp. Okay, and you can interpret this two ways. So this is the projection of X onto V, and this is the residual. Or you can say this is the projection of X onto V perp, and this is the residual. Okay, there's this duality, depending on what the space. Usually, like one of these spaces is more important for us. But from a mathematical perspective, there's a duality. So this representation always holds. Once you like pick V, you project onto V, you get X hat. By definition, the residual would satisfy this, because the residual is defined as X minus X hat, and E you know is in V perp. So when you write things like that, you have this nice decomposition. So every vector can be decomposed. If you have a V, there's a V perp, and every vector can be decomposed into two pieces, the sum of two pieces, X hat plus E, one component in V, one component in V perp. So the projection idea gives you a decomposition of this space. Okay, every vector is decomposed into two pieces. So you already know this, for example, in R3, every vector can be written as a component in XY plane, let's say, plus a component in the x-axis. Okay, so I can write every vector. In our case, that would be like that. In R2, for example, you can write everything as like a projection onto the x coordinate plus a projection into the y coordinate. So in R2, if this is V, this would be V perp, and everything can be written as uniquely. The idea is actually this representation is unique. So there's a unique vector in V and a unique vector in V perp, such that I can decompose every vector as the sum of the two. So the idea is that this holds for any general subspace. So it doesn't have to align with the coordinate axes. So I can pick, for example, in R2, I can pick this subspace, which is along the 1, 1, right? What will be the orthogonal complement in this case? It would be this, right? So would be what? -1 and 1. So I can write every vector as a summation of two elements. So one from this, the other from that component, like 1 minus 1, minus 1 and 1. Okay, so you can say this is like, I don't know, u plus v. Okay, so every vector can be written as the sum of two elements, one from this space, the other from that space, and this would be the projection of this onto that space. The other component would be the projection onto the other orthogonal complement. Okay. Yeah.
Is the dimension of the V curve is always equal to V?
That's a good question. So the dimension is dimension of, here the dimension of V perp is equal to V. How about here? This is V, like the V is XY plane. V perp is Z, like the Z axis. So what are the dimensions? Sorry?
So in that case, the dimension of V curve will be bigger than V.
The dimension of V perp is smaller, right? V is like XY plane, so dimension is 2. V perp would be the Z axis, dimension is 1. So the answer to a question is that in general, no, the dimension of V and V perp are not equal. They're actually complementary. So anyone can tell me what the relation between. So actually from this, you can sort of guess. First, this is written as, you'd see that I write this like mnemonically, like this is like abstract way of writing it. So I can decompose Rn into, this is called the direct sum. Doesn't matter the name, but just, this is like an advanced name, but it's just what we did. So Rn can be written as a direct sum of V and V perp. What does it mean? It just exactly means this. Every vector in Rn can be written uniquely as the sum of one element from V and the sum of one element from V perp. So the advantage of this is like just summarize everything. So if you like look at this, think what it means, you recall like what orthogonal complement means, what projection means, the idea of uniqueness, and then the idea of representation. So you can represent every vector as a sum of these two components. So from this, you should sort of see the complementary role that plays. So what is the dimension of, what is the relation between dimension of V and dimension of V perp? Can anyone guess what the relation is? Yes, exactly. So if you look at this, this suggests that the dimension of this side is n, is a dimension of V plus the dimension of V perp. That happens when you have the orthogonal sum, like when you have a direct sum. So this is saying that I can represent this as elements from this plus elements from that. The dimension of this is n. So it's like part of the space is constructed by this, the other part by that. So the dimensions sort of add up. This is not hard to show actually. But what I'm saying is this is suggestive, and you can see here. So dimension of the space, the full space is 3. 2 of it is picked up by this. 1 is picked up by that. So 2 plus 1 is 3. So dimensions are complementary. In this case, because the dimension of the space is 2, dimension of this is 1, the other one has to be 1 as well. Okay. So they just add up to the dimension of the whole space. Right. So in a sense, if you have a small v, the v perp would be big. If you have a big v, the v perp would be small. Okay. picks up whatever is left by V. Sounds good? Projection, so complement this decomposition of the space. It's just everything sort of boils down to the projection. So if you understand this projection idea, the rest is just sort of follows. Like they're just like easy consequences of this fact. Once you define the projection, then you get this decomposition. But like the decomposition of the space is a little bit, I would say, like slightly advanced. So if you just understand the projection, it's fine, right? So this I just mentioned because it's just helpful. So that just summarizes every vector x can be uniquely represented as a component in V, which I'm calling x hat. This is an approximation of x by something in V, and a residual, which is in V perp. Mnemonically, we write Rn is a decomposition of the space into V and V perp. And this decomposition is orthogonal. So these components, these two components are orthogonal to each other, right? By sort of definition. Questions? Okay, this proof is optional. You can read it for yourself. What it's saying is that here, what I'm trying to prove is that if the residual is orthogonal to V, then x hat has to be the projection. I'm not going to go through the proof. If you like, you read it. This summarizes the idea of V perp is V. Dimension of Rn is the sum of the dimensions. So dimension of V perp is n minus that. This one also follows from the orthogonality principle, which I'm going to come back to. So when we talk about regression, this is basically summarizes the regression from a linear algebraic point of view. Image of x perp is the kernel x transpose. So image of x and the kernel x transpose, they decompose the space. But I'm going to talk about that. This is something that we'll see later. If you believe this, then combining with the fact that dimension of V perp is n minus that, this gives you the rank nullity idea. Okay, so this I haven't proven. This sort of I waved my hand at the proof, but if you combine these two ideas, you get the rank nullity. We'll see this one later. Okay. Yeah, some of this is a little bit extra, I would say. So, but we really are going to use the idea of projection, and it helps a lot in getting the geometric intuition behind regression, which then helps a lot understanding everything, basically. The question about the idea of projection, the decomposition that we talked about, orthogonality principle. Okay, questions? No? So I'm going to come back to this later, so no worries. Just introducing or like recalling, hopefully. So the last thing that I want to talk about, like the second to last thing, is some properties of symmetric matrices that are extremely useful. The first one is the spectral decomposition of symmetric matrices. And another way of saying this is the eigenvalue decomposition of symmetric matrices, which I have written as EVD. So how many people know, okay, let me also tape this. So how many people know what this is? Like, what is the eigenvalue decomposition of a symmetric matrix? So how many people know what eigenvalues and eigenvectors are? Okay, 1, 2, hopefully more, yes. Okay, so any one of you wants to recall or like remind us what? So what are eigenvalues and eigenvectors? So I have a matrix, let's say symmetric for simplicity. What are the eigenvalues, eigenvectors? Yes.
We limited like discussion yesterday.
Okay.
So it's pretty fresh.
Great.
So,
Okay. So I'm gonna skip that now. Okay. So what are they?
It's like I said like ax equals like 1. It's like when you apply the transformation, it just like scales the vector.
Great. Yeah. So that's exactly it. So eigenvalue, it's easier to understand eigenvectors. So eigenvectors are, if you remember, so if you look at the matrix, let's say this is n by n, we use matrices as linear operators. So we think of matrices as acting on vectors and transforming the vector. So there's really a function, apply it to x, and it does something to x, produces an output. Okay, in this case, because it's n by n, so this is going to be n by 1. So the result is going to be, let's say y is going to be n by 1. Okay, so we remain in the same space. So these eigenvalue business makes sense if the matrix is square, at least. So we are transforming vectors from the same space back into the same space. So an eigenvector is a special vector such that when I transform it, I get itself back almost, but maybe a scaled. Okay, so scaled multiple of it back. So these are the directions that are sort of invariant under A. Okay, so X is an eigenvector. Lambda is the corresponding eigenvalue. So you can think of this as directions that are like, or gives, let's call this, if you want to be very precise, the span of X, okay? The span of X would be like the line that passes through X. So that line is preserved because this is going to be in the same line. It's not going to be exactly X, but it's going to be like a scaled multiple of X. So what I'm saying is like, if you work with this X, you pass it through A, you might get this, or you might get that, but everything is on the same line. So if you imagine, you're not going to leave the line, okay? So this is sometimes called an invariant subspace of A. It's invariant, it means that when you apply A2 vectors in this subspace, it's going to remain in that subspace. So it's the notion of invariance. So these are the directions that are preserved by A. And then once you, for a symmetric matrix, there are going to be n sort of independent directions. And because I know basically A does a very simple thing along these directions, and I can decompose every vector into like a combination of these directions, I know like exactly what A does. So it simplifies the action of A. Okay, so if I, so this is very simple. So if I give you something in along the X, you know what happens. So it's just multiplied by 2, for example. If I find another eigenvector, for example, this is another eigenvector. I know that, for example, A like maybe multiply things along this direction by 3, along this direction by 2. Now I can decompose every vector in R2 as like a linear combination of these two. And because A is linear, it passes through the linear combination coefficients, just I can determine what it does. So it's like, if it's like, let's say this is X, this is like Y, so Y is lambda prime Y, then A times alpha X plus beta Y would just be alpha AX plus beta AY, and this would be like lambda X. This would be what? lambda prime y. So you can see this would be basically, it's like lambda prime times alpha beta yeah, I don't want to write it as, but the coefficients are going to be like that. So yeah, this would be too complicated. Yeah, okay, let me do this, but you can get the action of A easily. Okay, so I'm just gonna, if I know the representation of that a particular vector in the basis, so x and y, let's say, are going to be a basis. Let's say x and y are linearly independent. Every vector in R2 can be written as a linear combination. Now, if I know these coefficients, I know what A does to it, because it just scales this coefficient by lambda, scales the other coefficient by lambda prime. So I get a new linear combination. And if you really think about this, you're basically transforming this guy to this. So if you look at the coefficients in terms of, if you look at the coefficients in terms of the coefficients of the basis expansion of a vector, these coefficients are transformed like that. So this is the diagonal matrix. So what it does is, like, in the basis of eigenvectors, the matrix or the linear operator acts like a diagonal matrix. So it simplifies everything to a diagonal operator. So if I have a diagonal operator, it's very simple. So if I have like a vector, like matrix, which is like 0, 2, I know what it does to a vector like xy. So it just multiplies the first coordinate by 1, the second coordinate by 2, say -1. Okay, so if this was my matrix, the action is very simple. To apply it to a vector, just rescale the coordinates. So this eigenvalue business, just generalize it to any symmetric matrix. So there is a basis. So this is vector represented in the standard basis. So x1 times 1, 0 plus x2 times 0, 1. So these are actually the eigenvectors of this matrix A. And then what you do is, like, you multiply this by -1. So this is going to be like negative x1 times 1, 0 plus 2x2 times 0, 1. So the eigenvalues of A are actually this and that. So this is like lambda x1. This is like lambda prime x2. So for a diagonal matrix, everything is simple. In general, what happens is that you expand any vector in terms of the general eigenvectors, and then the coefficients of that expansion are transformed by a diagonal matrix, which is basically this business. So every symmetric matrix can be sort of reduced to acting like a diagonal matrix if you choose the proper basis, which is the basis of the eigenvectors. Is that sort of? It's easier to actually do the more general case. You'll see. So what happens is, in general, is I can write every matrix A as like U lambda U transpose. Okay, so what happens is this is going to be like, these are going to be the columns. So the columns would be like, so that would be U, lambda would be lambda 1. Can we try? Add something here. So A would be written as U lambda. Every symmetric matrix can be written like this. In the end, the final story is U1, U2 to UN, lambda 1 lambda 2, that lambda n. These are the eigenvectors, sorry, eigenvalues, and then the transpose of this. So if I transpose this matrix, it's going to be U1 transpose here. So, and then U transpose here, UN transpose. So these are row vectors now. Okay, so the first one goes, so this goes here. The other one goes there. Okay. Second one goes there, and so on. So every matrix would have a decomposition like this, where the diagonal entries of that middle matrix are the eigenvalues. These U1s and U2 and up to UN are the eigenvectors. So U1 corresponds to the eigenvalue lambda 1, U2 corresponds to eigenvalue lambda 2. And this follows from the eigendecomposition. Yes.
This only works as a square, correct? Otherwise you
Yes,
can't
yes.
use eigenvalues?
Yes, yes, yes. And moreover, what I'm talking about is, like in this case, if A is symmetric, furthermore. Because if A is symmetric, you have this perfect decomposition. What happens is that you can always pick these U1 up to UN to be orthogonal to each other. Okay. This I'm not going to go into, but if the matrix is symmetric, I can always choose the eigenvectors to be orthogonal. So U's are going to be orthogonal to each other. And eigenvectors are really defined up to a scalar. So if X, for example, is an eigenvector, then 2X is also going to be an eigenvector, because A times 2X would be like lambda times 2X. It has the same property. So what people usually do is they normalize the eigenvector. So I can normalize them to have unique norm. So the norm of U1 is equal to the norm of U2. All of them are 1. So the norms are 1, and the inner products are 0 if I is not equal to J. Okay, so this is always possible if A is symmetric. And there's this correspondence, as I mentioned, that this eigenvector corresponds to exactly this eigenvalue. This eigenvector corresponds to this eigenvalue. So you order them according to their position. This one, for example, would be like corresponding to that. And so from this property that you can do, this matrix you can verify. Because the columns are orthogonal. If you remember, I had it, or we had an exercise. If you have, and all of them are non-zero because the norm is 1, they can't be non-zero. So we have pairwise orthogonal vectors, and they're non-zero. Okay, so they're linearly independent, if you remember. So they form a basis for this space. So this is the basis, a basis for this space. It's like a basis tailored to A. So if I want to understand A, I'm going to choose the basis, which is the orthogonal basis of the eigenvectors. And in that basis, A acts like this. What happens is that if I have an X, I want to see what A does to X, I have this representation. So this transfers X to that basis. In that basis, I do the diagonal manipulation, and I transfer it back to the original space. Okay, so this in the middle, it says the action of A in the basis of eigenvectors is a diagonal operator. Okay, so by doing this, when you multiply it, you basically take the U1 transpose X, U2 transpose X. So this would be like U lambda, this would be U1 transpose X up to UN transpose X. So this is like the component of X along U1, this is the component of X along UN. And then you rescale these. When I do that, I get U lambda 1, because it's a diagonal matrix, I get something like that. So I'm rescaling these. And these are now my coefficients. If you remember, if I have a vector, I've multiplied on the left by U, I'm just going to rescale, or like form a linear combination of these with these coefficients. So what it does is it just finds the components of X along these vectors, rescale them by the eigenvalues, and then use those new coordinates as coefficients of in this basis to construct. So this when you multiply this by u, you just form the linear combination of the elements of u by those coordinates, and that's what you have. So so this might, if you haven't seen it the first time, this is just a consequence of the idea of eigenvalue, eigenvector idea plus the idea of symmetry. So if A is symmetric, I'll always find this orthogonal basis of the eigenvectors. If you haven't seen it, it might be a little bit, I'd say like it takes a while to get used to. Well, while you get used to it, once you get used to it, you see that the composition basically reduces every matrix, symmetric matrix, to a diagonal matrix. So you can basically think of symmetric matrices as acting like diagonal matrices in a proper basis, which is the basis of the eigenvectors. This simplifies a lot of the arguments, or anything that basically has to do with the symmetric matrix. You can sort of immediately gain a lot of insight by using this decomposition. This is also an identity, so A is actually exactly equal to that. So once you multiply everything out, it's just that. So this summarizes all the discussion of the eigenvectors, eigenvalues into a nice compact form. A is U lambda U transpose. Lambda is diagonal, and U is going to be what is called an orthogonal matrix. Orthogonal matrix. So what it means is exactly this, that the columns are unit norm, the norm is 1, and they're orthogonal to each other. This property translates to this property, which you can verify. U transpose is equal to U transpose U is equal to I. Just saying that U inverse is U transpose. So the inverse of this, so this is basically the inverse. So if this is U, this would be the inverse of U. You can multiply this by that, you can see that you get the identity. So there's a lot of things going on here. But that's it basically. This slide just summarizes everything. Okay, so from the notion of eigenvalues and eigenvectors, we get to this idea of an orthogonal decomposition of a symmetric matrix, where it can be written as an orthogonal matrix multiplied by a diagonal matrix multiplied by transpose of that orthogonal matrix, which happens to be also the inverse of that orthogonal matrix. And this decomposition is helpful to make every symmetric matrix basically act like a diagonal matrix. Sort of sounds good. Okay. So this just summarizes. There is a corresponding decomposition for rectangular matrices, which we don't go into. But if you're interested, it's called singular value decomposition, SVD. So this one I called EVD. The other one is SVD, and it's closely related to this. So you can decompose every rectangular matrix in terms of orthogonal matrices and diagonal matrices. It's very useful, so I encourage you to go look it up. But to avoid further confusion, we're not going to talk about it in this course. So here's a very simple example. So I have the symmetric matrix. The eigenvalue decomposition, I have written it here. Okay, so there is this eigenvalue decomposition. So what it means is that what I'm claiming is this is an eigenvector corresponding to eigenvalue 3. This other guy is an eigenvector corresponding to eigenvalue -1. And then you can see that this guy transposed goes here. This guy transposed goes there. Oh, sorry. There's just the same thing transposed. I haven't transposed it. So I put a transpose here. So it's just U. That's U. This is U as well. In any case, you can verify easily that this has 2 eigenvalues. So I suppose you know how to calculate the eigenvalues of a 2x2 matrix. If you don't, review your linear algebra course. But you can find the eigenvalues, and you can also find the eigenvectors. Once you have the eigenvalues, you can solve a linear system of equations to find the corresponding eigenvector or eigenvectors. I'm not going to talk about how to actually numerically calculate, but you can verify that there are these 2 eigenvalues, and then I can pick these eigenvectors. Okay, The eigenvectors usually that you get is like maybe you show that the eigenvector is actually 1, 1. So it's easy to show, for example, that 1, 1 is an eigenvector. So if I multiply, I get 3, 3, which is just 3 by 1, 1. So this shows that this is an eigenvector corresponding to eigenvalue 3. But what I'm doing here is I'm normalizing. Okay, so I'm dividing it by its norm. So if I have this vector, so what is the norm of 1, 1? Norm? Yes. Yeah, so it would be like root 1 squared plus 1 squared, which is root 2. So if I divide this by the length, the norm of this you can verify is going to be 1. Okay, so that's what I'm doing. So you calculate maybe you end up with this, or maybe like whatever you end up with, you normalize it, you divide it by its norm. That preserves this being an eigenvector, but then the norm of this is going to be 1. The same goes for this. This is like 1 minus 1, basically, if you want to be simple, but then I divide it by the norm to make this an orthogonal matrix. So the same goes for this matrix. This sort of has similar eigenvectors, but the eigenvalues are different. Okay, so you can see the eigenvector corresponding to 2 is this negative 1 and 1. The eigenvalue corresponding to 0 is 1 and 1. So the eigenvectors are similar, but they do different things on the diagonal. Okay, so the matrices are not the same, but in terms of the eigen decomposition, you can see the basis is sort of the same. Just you order it, so this corresponds to that. This is the same, but the eigenvalues are different. So one of the things that this decomposition gives you is immediately you can see the rank of the matrices. Okay, so anyone can tell me the rank of, sorry? 2 and 1, yeah. So from like this, you can also see it's easy because this is a like multiple of this one. So the rank in this case is 1. This is sort of also easy to see that they're linearly independent. But it's easier to see from this diagonal because these are orthogonal transformation. The rank is preserved by orthogonal transformations. So the rank of A would be the same as the rank of this middle guy. The rank of like the symmetric matrix would be the same as the diagonal matrix, which is in the middle. And the rank of a diagonal matrix is just the number of non-zero elements in the diagonal. So the rank of this is 2 because there are 2 non-zero elements here. The rank of this is 1 because there's just 1 non-zero element. Yes.
So the rank is also the same as the number of eigenvalues?
The number of non-zero eigenvalues. For a symmetric matrix, the rank of the matrix is the number of non-zero eigenvalues. This you can easily see from this representation, actually. Okay, so there's a lot that you can do with this decomposition, but because this is not a linear algebra course, I don't go into much of this. Like at the bare minimum, what you need to remember is that every symmetric matrix can be written like that. Where U is an orthogonal matrix, lambda is a diagonal matrix. Everything else follows from that. And that these are related to the eigenvalues and eigenvectors. Okay, so diagonal elements are the eigenvalues, the columns of U are the eigenvectors. That's it. Okay, that's the like punchline. So all of these things that we worked through, there's a punchline. If you remember the punchline, there's like the whole story sort of follows from that punchline. Okay, every time you like see a symmetric matrix, if you want to do like analytic work with it, it's worth thinking about what eigenvalue decomposition can tell you. It often tells you a lot of information. Good. Okay, one more thing. So there's a special class of symmetric matrices. They're called positive semidefinite matrices. And how many people have seen positive semidefinite matrices? Okay, so these are within the class of symmetric matrices. So a symmetric matrix is called positive semidefinite if XAX is like A inner product with AX is positive, but non-negative. So AX is transformation of X. I pick an X, like a vector X. AX is the output of linear transformation applied to x. So if I take the ax and take the inner product with x, is positive. So it's like almost in the same direction. Not exactly the same direction, but it's like they form it's like an angle which is less than 90 degrees. Okay, or at most 90 degrees. So if this is x, this would be ax. It wouldn't be like this. So for every vector x inner product with ax is non-negative. If you remember what the inner product is, you can write it as x transpose ax is non-negative. So a matrix that has this property that whenever you have any vector x transpose ax is non-negative. This is called positive semi-definite. If it happens that this is strictly positive for any non-zero vector, it's called positive definite. So if I have this inequality, whenever x is non-negative, it's called positive definite. So positive semi-definite means there's a possibility that this is zero. Positive definite means no, there's no zero possibility. It's just strictly positive for all non-zero vectors. That's the definition. It's again like maybe a little bit abstract, but the sort of intuition is that these matrices behave like positive numbers. It's like the operator level version of positive or non-negative numbers. In particular, they have square roots. That's what I want to talk about. But another characterization for symmetric matrices, because I told you that everything about symmetric matrices can be reduced to diagonal matrices by the eigenvalue decomposition. This is the definition, but you can show it's equivalent to saying that the eigenvalues are all non-negative. So positive semi-definite matrix, which I say PSD. A PSD matrix is a matrix whose eigenvalues are all non-negative. A positive definite matrix is the one whose eigenvalues are all strictly bigger than zero. Okay, so in terms of eigenvalues, the story is very simple. For example, is this matrix positive semi-definite? No, because there is a not negative here. So is this positive semi-definite? Yes, because the eigenvalues are positive. You can see the eigenvalue in terms of the eigenvalues is simple. If you want to verify this inequality, it's harder. It's not obvious. So you have to write down this like x1, x2, transpose this matrix and x1, x2, expand, and then try to say that this is always non-negative for any x1 and x2. Yes.
So we're doing greater than or equal to zero, right? Just non-negative. Does it have to actually be positive? So zero is okay.
The difference is like the PSD versus PD. So this is so this matrix is PSD, but not positive definite.
Oh, okay, because of the zero.
Yes, yes. So if all of them were strictly bigger than zero, it would be positive definite. This is not even a PSD, not PSD. Okay. So a consequence of like an interesting property of a positive semi-definite matrix is that there is a symmetric square root. So if you remember what a square root of a number is, so what is the square root of a number from the elementary school? The definition of the square root? Yeah.
Multiply by itself and get back to the
Yeah, so basically if I want to take the square root of x, first it has to be non-negative, unless you know about complex analysis. The square root is something that if I multiply by itself, it gives me back x. So the square root of x is something that whenever I multiply it by itself, it gives back this. So I can define it for the matrices. So if I have a matrix here, like symmetric matrix, I want to find a matrix such that if I multiply it by itself, I get back A. Okay, this is a little bit more tricky because matrix multiplication is not that simple. It's like a non-intuitive way of multiplication is defined for them. But this notation just means that, so there is some B such that if I multiply by itself is going to be A. So the solution of this, in other words, like B squared is A. If I can solve this, if there is a B that satisfies this, that would be a square root. There might be multiple B's that satisfy this. What I'm interested in is like, if A is symmetric, is there a symmetric matrix that has this property? And the answer is yes, there is a symmetric matrix. which I'm going to denote by either root a or a to the 1/2, and it has the property that a1/2 times a1/2 is equal to a. This exists for any positive semi-definite matrix, and it's actually easy to calculate it based on the eigenvalue decomposition. If the eigenvalue decomposition is like that, then it is easy to see that the square root is calculated by taking the square root of the diagonal matrix inside. And this is just for a diagonal matrix, the square root is very simple. It's just square root of the elements. So you take the square root of the elements and leave everything else intact. So this u remains. You just take the square root of the diagonal matrix in the middle. That would be the square root of a. Why this is the square root of a? Because I can verify this identity. So I want to calculate a1/2 times a1/2. It would be u lambda 1/2 u transpose times u lambda 1/2 u transpose. So matrix multiplication, I can just drop the parentheses. I can multiply in any order I want. So I'm just gonna drop the parentheses, u lambda 1/2 u transpose, u lambda 1/2 u transpose. I'm gonna first multiply these two. Anyone remembers what these two are? Yes. So u transpose is u inverse, so this is gonna be identity. Right. So identity I can just ignore in matrix multiplication, so I get u lambda 1/2 u transpose. Basically identity times, you can say I'm multiplying this by that, I get lambda 1/2. So lambda 1/2 times lambda 1/2 would be lambda. It's very easy to see that if I multiply a diagonal matrix by itself, it's just going to square the elements. So this is A. So this proves the idea. You can see that orthogonality really helps here. And so this is the first indication that these eigen decomposition is very useful. So you do this, you take the square root of the middle, you get the square root of the matrix. Okay, so you put things back together. Okay, sounds good. So we talked about projection, spectral decomposition, symmetric matrices, and positive semi-definite matrices. So that sort of concludes our discussion of linear algebra. And next time we're going to talk about random variables. Okay, thank you guys. See you next time.